Hello, everyone. I make that the top of the hour. Thank you very much for joining our event tonight. I did say if you're my side of the pond, grab a beer or a wine. I'm afraid I'm going to let you down. I'm having a tea myself, just to give an aura of professionalism. So thank you very much for joining. I'm Rob Reid, Cockroach Labs technical evangelist, and tonight I'm joined by Dipti Joshi, our very wonderful and very talented staff product manager here at Cockroach Labs. Dipti, thank you so much for joining.
You're welcome. I'm glad to be here.
So Dipti and I will be talking about a bunch of things today. We'll be giving you an introduction to distributed SQL, much like almost a year ago, I gave an introduction to distributed SQL, but we're going to lean in a bit more on the agentic side, as is on trend at the moment, and scale, especially scaling for that agentic workload. We're going to be touching upon things like resilience, consistency, locality, and scale. And then Dipti's going to give us a deeper dive into Agentic Scale and how CockroachDB is prepared for that. If you have any questions at all, you'll see that the chat feature is probably disabled, but the Q&A feature isn't. So if you have any questions, just fire them away and Dipti and I can get to them as quickly as we can. So I have a question for you, Dipti. What is your favorite feature of CockroachDB? I always like to ask this question because I have my own favorites, but I'm always interested to find out what other people's are.
I really like how CockroachDB offers data locality with its multi-region support.
Yes. To me, that's always felt magic. I remember when the product first gained the ability to geo-partition, and although it was clunkier than it is today, there's a lot of, nicety and abstraction on top of it. It's incredibly powerful, and it
Yes,
feels like cheating.
yes, yes.
Well, thank you all again. Remember, any questions, just fire them in. There's no bad time. But we're going to start by flipping the tables a little bit. So we have a question for you. It's a polling question, which will probably pop up on your screen anytime now. There it is. And essentially, it's what is your peak QPS or queries per second, requests per second today? And this could be your busiest application, or it might be across your entire application estate. Thinking production here. If you could answer that, give us an idea as to what kind of QPS you're dealing with now, and also what you expect it to be like in between 1 and 2 years. Now, I'll keep on moving along, but keep your answers coming in. So we'll start with a quick introduction to distributed SQL. And the reason for this is since the 70s and relational databases were first introduced, then over to 2008 when the term NoSQL was coined, all the way through to cloud augmented databases, and finally distributed SQL databases, we are on a trajectory of scale. And distributed SQL marries together all the things we have known and loved and come to respect of relational databases and pairs them with both cloud scale and the extreme sprawl of the cloud, but also the scalability of NoSQL. So we're going to go through the tenets of distributed SQL now, of which there are four main ones. First is resilience. And now resilience in a database should be built in. It shouldn't rely on external tooling or processes, and recovery should be automatic and immediate. The next is consistency. You should have a consistent view, or rather your users should have a consistent view, human or otherwise, of your data. Writes should always be right. And that extends to great distances. Regardless of how big your database becomes, you should always have a consistent view of your data. It should also be easy to geo-partition your data. That simply means place data close to users for reasons of read and write performance, but also for reasons of regulatory requirements, of which there are many, and there are many more, it seems, every day. And finally, scale. It should be easy to scale both up and down, elastic scaling. Scaling shouldn't incur downtime or maintenance windows, and data should be rebalanced as you scale. I'm talking about the opposite of manual sharding here. So let's go a little bit deeper into resilience to start off with. So historically, when people talk about resilience, this is what they're talking about. This is probably best case scenario in a traditional database that uses business continuity. So this is keeping their business online in the event of a disaster, hence disaster recovery. But the issue I have with disaster recovery is it assumes that a disaster must have first occurred. for you to recover from. So in this example, the primary goes down for any reason, and at this point, your production traffic, your production applications are offline. Hopefully, you have monitoring in place, PagerDuty, etc., and you're made aware of this before your users are. At which point, you begin a failover process from the primary to the standby. This is a risky process, which is why companies tend to only test their failover processes every so often. Once the primary comes back online, you can then fail back. But unfortunately, this process does introduce high RPO, or recovery point objective, that's simply data loss, and high RTO, that's recovery time objective, that's downtime. And it all comes down to reacting to issues that have already occurred. Best case scenario, this is what your legacy database might look like. It's worse if you don't have a standby database to fall back on, because then you're in the world of backup and restore, which can incur much higher RTO. You're hearing a lot of echo. Dipti, are you hearing a lot of echo?
I do not.
But thank you for letting me know. Okay, well, if you are, let me see. I'll move back a little. Okay, there's someone else who said no echo. Well, I'll continue on the basis that hopefully most people aren't hearing a horrible echo. But for those who are, I'm very sorry. Oh, we have a question that's not related to my echo. Okay. So, does CockroachDB OpenTelemetry Collector support OTEL or OTEL for all instances of CockroachDB? I honestly wouldn't have the answer to that. Is that a question that you have the answer to, Dipti? I know you do a lot of performance testing and monitoring. So do you know much about OpenTelemetry in CockroachDB? Oh, you're on mute, Dipti.
I know that we support it.
Yeah.
Like we can follow up with documentation links about it.
Yeah, that sounds good. Yeah, apologies, I wasn't able to answer that. If there's any Cockroach Labs people on the call, feel free to let us know in the Q&A. Cool. So this is what we talk about at Cockroach Labs when we talk about resilience. A cluster is healthy. All of the nodes in the cluster are running healthy, but it's the ability for a node to self-heal when it detects, or when the cluster detects, an issue. And I'll talk about the types of issues that we detect in a minute. And this happens before your customers detect a problem with your application. It happens at machine speeds. So for example, if we were to lose node 2, for example, and that's down, the cluster is still healthy. We still have a majority of nodes online. We still have quorum in the data. When it comes back up again, the nodes that survived the outage replicate their data back to node 2 just to keep it back up to date. This is what you missed while you were down. And oh my goodness. And because of this, there's zero RPO, zero data loss. Your data is always going to be safe in CockroachDB, and there's minimal RTO. On average, I think it's about 4.5 seconds, worst case, just to survive and recover automatically from an outage. However, those of you familiar with Murphy's Law will appreciate that it's not just nodes that can fail. Anything that can go wrong will eventually go wrong. The physical disks that house your data could become corrupt. A heavy particle from space could slam into a bit and flip it. These kinds of things do happen. Network nodes go down, but buildings also go down. And if you look back to 2012, most of India went down, 10% of the world's population at the time. Now, networks can also fail. They can fail both unidirectionally, that's an asymmetric network partition, or bidirectionally, which is less insidious than an asymmetric network partition. Entire regions can go down, and so can cloud providers. So thinking about any of these issues, not only at the moment will your human users need to stampede your system in order to, continue where they left off, but if you're running agents against your system, they too will also stampede your system, which could cause further problems. Your systems should also be resilient to change. The database you're running today is very likely to resemble the database that you were running 5 years ago. And it's probably even less likely that that database will represent today's database in a year or so. And unless your database is able to run schema changes, that's changes to your tables, to your primary keys, indices, etc., you're going to have to take your database down in order to run those changes. And this is a real world example of an online schema change running against a live production cluster in CockroachDB. You can see that prior to an index optimization, you don't need to know exactly what table it is, but you see the index is applied and the CPU drops from a range of around 50% to around 15%. And that was running, this is from the same time period. We're running around, it looks around 5,500 requests per second on average. And the service latency absolutely drops from around 60 milliseconds to around, it looks about 10 to me. So that was a utilization decrease of 60% in this example, and a latency decrease of around 9 times. The next thing is a database should be consistent. Now, given this example, this is an example of a manually sharded database, or perhaps a database with a primary writer, which is common for a lot of cloud databases, and read replicas. Now, a user in the middle writes a value to the primary or writer node. That might be $1,000, let's say. And that's asynchronously replicated to any of the read replicas. Now, depending on the read replica that your request hits, when you hit through that load balancer, you could see $1,000, but you could see a previous value. So your data isn't guaranteed to be consistent in this example. This is where read anomalies occur. Now, that's human users, and they're operating at human speeds. But agents work much faster than humans. They don't wait they don't wait on the same things that humans wait on. They don't stop to think necessarily. And the chances, therefore, that they'll encounter stale data are much higher than your human users. And AI hallucinates, as we all know, with good data. Strong consistency is necessary to prevent catastrophic cascading failures as a result of poor consistency in your data. And practically speaking, if your agents are going to hallucinate, you should at least make sure or strive to make sure that they're hallucinating from the same reality as each other. Conversely, in CockroachDB, because the distance between these nodes might be the same, because we might be replicating data across regions or availability zones, so they're not guaranteed to be, the same distance apart, but they are guaranteed to have the same view of data. And that's for all users talking directly to the database and any users getting their data from our transactionally consistent built-in CDC or change data capture. Now, this QR code down here, feel free to scan it, but we will be sending the slides out probably tomorrow. We'll have is a demo link of me running through an agentic fraud detection scenario that is primarily driven from CockroachDB CDC. Next is locality. Now, this is going on to Dipti and actually one of my favorite features of CockroachDB. And that's the ability to geographically partition data in a very easy way. So it's actually a lot more straightforward than you might think. I've had the unfortunate experience of working with databases that weren't CockroachDB in a global capacity, and it was actually pretty difficult to work with. Now, there are things to keep in mind when you're running a globally distributed database. Latency becomes an issue because you can't beat the speed of light. And there are many data regulations that you need to adhere to. For example, if you're in the EU and your data spans both the EU and the US, you need to be aware of Schrems 2, which stipulates that data from the EU can't cross the pond without prior consent from the data subject or the individual's data. But we make it easy to partition data for various workloads, and I'll talk about some of the topology patterns now. One of those is global data. Now, this ensures that for a globally distributed database with multiple regions, everyone is going to see the same data. Now, this is great for reference data or data that doesn't change very often because you're going to pay the price on write latency. A write is guaranteed to be consistent across all of these regions, so your request will take upwards of 100 to 200 milliseconds, depending on how far your cluster spreads. Now, everyone, as an upside to this, gets immediately low latency. So if you're doing things like translations or currency conversions that might only change once a day, that's a great case for global tables. And this is how to create them. In this example, we have a product. We have an ID, a name, and a price. the price might change occasionally, but if everyone needs to see the same product data, there might be translations against that for different markets, perhaps, but everyone's going to get good read latency to this. The next is our two regional partitionings. So the first is regional table, and that will ensure that, well, let's go on to that in a minute. I'll show you the regional by row first, because this is, I think, quite magic. So in a globally distributed database, you might want to ring fence some of your data for the US. You might want to ring fence some of that data for the EU, and you might want to ring fence some of it to Asia Pacific. Now, this is at a high level. You might then want to sub-partition lower levels. So you might want to have West Coast data partitioned, East Coast data partitioned, etc. But on the whole, this satisfies a lot of the regulations that you'll come up against when you're dealing with sensitive payment, healthcare data, etc. Now, this also matters in the world of agentic AI. If you're training, well, just ML in general, if you're training models, that data will also be subject to data regulations like GDPR. This is how to create a regional table. Now, for data that needs to only exist in one particular region, let's say in this example, we've got a staff shift data. Maybe all of our staff are based in EU Central 1, that's Frankfurt. Because we're only manipulating staff shift data from Frankfurt, perhaps, the data doesn't need to exist anywhere else in the cluster. So you can say that this table should be pinned to Frankfurt. Conversely, if you want data to be close to wherever the users are that are consuming your tables, they might be in Frankfurt, they might be in the States, they might be in Singapore, you can make it regional by row. And every row in the table will therefore have a region assigned to it and will be physically stored in separate disaggregated places, but it's all still centrally managed. There is a question that's not relating to my echo. You may have multiple no, it was related to my echo. You may have multiple microphones, both Zoom and native computer audio, quite possibly, but hopefully it's all right. I haven't heard any more complaints since the first one. Next are the complexity challenges. So the complexity of trying to distribute a non-distributed SQL database can't be understated. I've experienced this myself firsthand in production. And now with the growing hunger for AI and vector data, unless you're running a distributed database that unifies both SQL and vector database, you risk adding an enormous amount of complexity into your architecture to keep up. And this slide will explain that in a second. We have a question. What happens to regional local table if the region goes down? Good question. So if you have a regional table like we did in our Frankfurt example, and the Frankfurt region would go down, you would lose access to that data until it became online again. Because all of the nodes that house that data, if you've specifically locked it with what we would call a super region, you wouldn't have access to that data. Now, more realistically, depending on the number of regions you're running, you can have multiple regions within a super region. So that data, if it's possible to do so, you might also replicate that data to maybe Helsinki and Paris and have a super region around those three regions, such that if the Frankfurt region goes down, the data is still safe and online. And we've got another question. I'm currently using Google Spanner, which uses linealizable for consistency. I understand that CockroachDB uses serializable. Can CockroachDB give strong consistency for real-time use cases? Yes, we offer our default method of operation or default isolation level is serializable. So you're guaranteed that there aren't going to be any read or write anomalies present. Now, we do also support read committed, and we offer that for a number of reasons, but primarily to help users who come from Postgres, whose default isolation level is read committed. With serializable and pessimistic concurrency control, which we employ, you're more likely to see retry errors if the data that you're trying to manipulate has changed since you tried to start manipulating it. I hope that answers your question. So back onto the complexity of managing and the need for unifying SQL and vector data. So let's say we have both relational and vector data. but we haven't yet unified them. Maybe we've got a regular SQL database over here. Many databases actually now support vectors, but let's assume you didn't know that and you've separated your concerns. You're going to have to implement some kind of ETL pipeline to funnel that data, massage that data from your SQL database into your vector database. Now, that's the case for the US. You might also have a presence in the EU and Asia Pacific. Now, that is 3 separate pipelines, all working distinctly from one another. Now, you might also need to gain a holistic view of your relational, transactional, and vector data. So you'll also need some way of funneling that data into these central stores to gain that holistic real-time view, or at least near real-time view of your entire business. That was a problem I had when I was running 17 disparate instances of the same application stack across various areas of the world, because the application architecture had grown organically over time. And this is pre-distributed SQL. And finally, we get onto scale. So many of you all know this is what vertically scaling a traditional database looks like. Let's say we're running a single node for our reads and writes, and there's 4 CPUs, 4 gigs of memory, and 10 gigabytes of disk. Now, if you need to scale that up, you turn it off. Maybe you don't have physical access to it. Maybe you're doing this in the cloud, but historically, you have a machine sat somewhere. You turn it off, you open it up, you install everything you need, you turn it back on, and at that point, your maintenance window's over, and everything comes back online again. You've got a beefier box. The same goes for further scale ups, but also scale downs. You need to open the box, turn it off, maintenance window, install your RAM, tinker with the motherboard, whatever you need to do, and bring it back online again. Now, again, you might not have physical access to this box, but the same story holds. If you horizontally shard a database to gain horizontal scaling, which I've also attempted, much to my mental detriment, this is what it might look like for you. So that same 4 CPU, 8 gig memory, 10 gig disk can be split into 2. And at that point, you're sharding your data. Now, anytime you shard data, that needs to be a very long-lived partitioning key. But if you need to then reshard to scale up again, that's another shard. And you have to shard potentially at multiple levels using, I think it's called native partitioning, for every table in every region. So it becomes a maintenance overhead. If you need to scale back again, so if you want to provide elastic scalability, that's yet another shard. Now, my experience with this is, and I've actually got a recording of this, there's a demo of me suffering through the process of this. I was using Postgres. I was using the foreign data wrapper extension from Postgres because I thought that might make my life a bit easier. I had a single table with multiple sharding scenarios. One was a scale up, and then another scale up, and then a scale into another region with sub-partitioning from there. But ultimately, after a week of hard work, I was left with a completely broken database. Now, this is what scaling up looks like in CockroachDB. Scaling up and down is one of the more obvious benefits of a distributed system. And actually, under provisioning is an over provisioning are some of the things you can avoid when running a distributed SQL database. So you can start small and grow as you need. So in this example, we have a 3-node cluster, very similar to the one we had before. And with replication, 3 ways across the cluster, we're looking at about a total storage of around 14 gigabytes of replicated data and 12 vCPUs. To scale up, you simply add new nodes to the cluster, and that will be automatically reflected in the CPU, the memory available to the cluster, and the total amount of storage space. To scale down, it's just as easy. You ring fence the nodes that you want to decommission, and CockroachDB handles the rest. It turns them off, it drains them first, it reallocates data or rebalances data to the remaining nodes, and it turns them off. This is what it looks like for our customers. And these are some real world numbers from various companies across different verticals, just to show you the kinds of scaling they're doing. So a betting company, you've all heard of it, runs 30 nodes of 32 vCPUs, totaling 960 VPUs for their general betting activities. But the Super Bowl, they scale up 233% every year to 100 nodes, up to 3,600 vCPUs. And then they're able to ring fence the 70 nodes they added for Super Bowl and simply decommission them. And CockroachDB handles the rest without any impact on their foreground traffic. A retail company goes from 18 4 vCPU machines to 27 16 vCPU machines. That's 500% increase for Black Friday. They scale back down again right after. I've been in a situation where I've had to manually scale up a database and manually scale it back down again. And I had to do that long before the scale up period was required. This was Christmas in my case. And then because it required downtime, I waited long after Christmas at great expense because I didn't want to damage the system. A gaming company scales up 100% for every new release they do. And finally, a SaaS company, while they might only be scaling up 14% from 8,400 vCPUs to 9,600, they do so every day. However, unless you've been living under a rock, you'll know that humans aren't going to be the biggest stressor on your systems forever. And this is a typical architecture where users are interacting with an application, simple client server kind of thing that interacts with a database. Now, that's your humans. Your agents are likely to, in a many orders of magnitude, dwarf the human traffic eventually. So with that, I will pass over to Dipti, who's going to talk a bit more about agentic readiness in CockroachDB.
Thank you, Rob. Your talk about the agentic scale is a good segue in this. Is as we know, the reality of the world is agentic now, and what you see here is we did an analysis of our various customers across various different use cases. These of what their workload is now, and based on their workload trend, where they will be in 2 years or 3 years. And as you can see, some of these, like many of them are at like million QPS, and some of the larger ones that we have is like, especially those which are like object metadata for agentic workload. As you can see, this one is like we are projecting it to go to 100 million QPS. Right now they are at 1 million. Their next year will be 10 million, and 3 years 100 million. Same way, a couple others like here 16 millions. And these workloads are different. Like some of the gaming workloads there, they are more like read and then read heavy. Some of the workload are read and write, and some of the workload are more on the right side. But still, at all different workload, we see that the scale is growing, and so we want our customers to be able to handle that as they grow. And we want to be there before they are there, so that when our customers, our users, when they grow, we are already ready there for that. So we started on a agentic scale readiness initiative. Next slide, please.
Yeah, but I'm fascinated by this, Dipti, because the idea of running a database with 100 million requests per second just seems so astronomically different to anything I've heard before. But it's easy for me to picture what 100 million requests per second might look like in it, because I work for a distributed SQL company. If I was running a traditional database and I was hearing 100 million potentially for a very successful company running against agentic workloads, people are in trouble here, I think. Before we move on, what's the biggest customer cluster in terms of node count that you're currently aware of?
The one we have is 240 nodes, but it is growing.
Oh,
We
wow.
had another customer that we are projecting they will go to like 400 nodes, and so we want to be there before them. So
Yeah,
this is why we are getting ready for an. That's a good segue into the next
it
slide
is.
also, how we
Yes,
did
let's
the
do it.
readiness,
Yeah.
right? So uh, we did not like do this today. We have been working on this for last 1.5 years, and we started this initiative 1.5 years ago, and then every major release, we do a scale assessment, and every quarter we do, but then every major release we do scale assessment that we actually use it as our milestone. So in November of 2024, we started with 150 nodes based on the reality at that time of where our customers are, what we are seeing in our prospects, and 225 terabyte on our 24.3 release, which was the latest release. And we were able to get a peak throughput of 950,000 TPMC. TPMC is the TPCC transactions per minute. We chose TPCC because TPCC is like 60% write, 40% read. So it gave us a good balance. And for OLTP databases, it's a good benchmark. However, all this workload was not just running like in ideal condition. This workload runs in realistic condition. And I'll talk about that in next slide, but let's talk about what we did next. So then last year we did 300 node assessment, but this time we said we are going to go 1.2 petabyte. Instead of like doubling from 225 to 500 terabyte, we said, because that's the trend we were seeing. And on our 25.2 release, and we were able to get a peak of 2.1 million TPMC. And then in 25.4 at the end of the year we did. And we have a blog that we went online last week. And we achieved 2.2 million TPMC. And this, again, you see like between the 300 node 25.2 and 25.4, the improvement that you see in TPMC, because while we have the scale initiative going on, we also have a big initiative going about performance improvement. And this shows that performance gain that we get from release to release. And going back to the point of where I said, this was not just in like isolation, ideal workload condition, but this was in reality condition, because that's what our customer, see. And also we have a benchmark called PUA. If some of you have not seen it, you should go to our website and visit it. There we published 9 node and 15 node, but this was done at same thing at 300 node scale. So let's look at what we did next.
Yeah, before we do, I think it makes sense to call out this is TPMC requests, not requests per second. Is that right?
Yes.
Because
Yes.
each transaction in a TPCC transaction actually involves about 9 queries. So where we're looking at 2.2 million requests per second or transactions per second, we're actually looking at closer to 18 million. Well, over. Is that right?
So this is per minute. So transaction per minute. That's how TPCC standard.
Oh, per minute. So 18 million per minute. That's
yes, per minute.
ridiculous numbers.
Yeah.
Yes, sorry, I won't. What kinds of? So I've run clusters myself. I've run 3 node clusters for demos. I've run 15. I've run 27 node clusters.
Yeah.
And at those scales, and I think Google actually also say it, when you're running at Google scale, failure no longer is a question of if, it's when. What kinds of issues can people expect to run into when they're operating at 300 nodes? Now, obviously, CockroachDB is inherently very resilient and automatically heals from these kinds of things.
Yes.
But what's going on under the covers? What are people being protected from at these scales?
Yeah, so at this scale, if you see on a per node level, the traffic is each node is probably experiencing, about roughly same traffic. Where the traffic workload happens is on the network, because you are doing a lot of gossip going on. And also when it is the operational and observability aspect of it, it's not just about running workload, but to be able to do rolling restarts, to be able to do like upgrades, to be able to do backup and restore of at this scale. And those are the challenges that one can come across, and that is the reason why instead of ideal world condition, we said we are going to do it in realistic condition, because that's what our customer face.
Yeah, so. And talking about that is a very nice segue to the next one.
Yeah. So again, as I said in the previous slide about our performance under adversity, this was not done in isolation. We ran this scale assessment on a 300 node and to standard GCP node, which is 16 vCPU node, and with 2 terabyte per store. And there are 2 stores per node, and which comes to 1.2 petabyte of total data storage capacity. And the workload we were running is TPCC workload. And initially, we loaded 4 million warehouse worth of data in it. And then we started a workload that where at any time 266,000 active warehouses will be queried. And we ran this for 10 days. And so over 10 days, the data was growing, as well as what else was going on. We were running backup and restore. There was nightly full backup and hourly incremental backup. We were continuously running change feeds. So because it's not, you don't just sit in isolation in a data ecosystem. Especially when you are system of record, there are other downstream data system that needs data from you. So we had those change feed going on. We also did a huge schema change on a 121 billion row schema table. We did a schema change, and we were able to do this in 18 hours, which if you think about 121 billion rows, that's a lot. That's a lot.
I struggle to think about 120. I struggle to think about a billion rows, let alone 121 billion.
And again, these are like, operational activity that happens. But in reality, there are things going on. As I said earlier, like, things that can happen network. You can have network partitions. That's not in your control. You can have node failures, nodes can fail, or you may want to do just, operational rolling restarts. You can have distalls. These are very common distalls. What distalls is, especially in cloud environment, is where you think you have provisioned your bandwidth and IOPS, but in reality, you do not get your 100% IOPS and bandwidth all the time. That's because cloud provider over-provision them. And as a result of that, when you're not getting that IOPS and bandwidth, your application is going to experience like a distall, like your database layer. And so your write is going to wait, and then, there's going to be all kind of timeouts and failures of transaction, all that happen. And then that will impact your, throughput also. So we observe about 20 to 30 distalls per hour. And it's not just one cloud. We have seen it in AWS, we have seen it in Azure, we have seen it in Google. And under this kind of chaos condition also, while you have, your internal administrative task going on that generates stress on the system, you have external out of control chaos going on. This steady state SQL QPS and latency remained same as the baseline. So it sustained the latency and throughput under the internal stress and chaos. And this again goes back to what I said, performance under adversity, that we are not just talking about performance under adversity at 9 or 15 nodes, but also at scale. And because at agentic scale, as you said earlier, you are going to see a traffic surge of according to Gartner, you will see about 1,000x traffic surge.
1,000.
Yeah. And so we need to be ready for that. And under this, and that's why we are starting this early and not waiting till our customers hit them.
Dipti, we have a question. What do backup strategies look like at this kind of scale? Is it a second cluster? Is it CDC? What kind of mechanism is being used here to perform those full nightly backups and the incremental backups in between?
Yeah, so the backups were being done, and the destination of the backups were GCP storage device. So it was not going to another cluster. And the reason why you do not have to send to another cluster, because CockroachDB is already resilient. We already have at least, replication factor of 3. And as a result of that, if you lose a node, you are going to have other 2 nodes, and somebody else is also going to become a member of that range. So we were backing up to a GCP storage, and then which was happening, like as I said, full and incremental. And then we did one exercise of the restore also, because you're not only able to do backup, but you should be able to restore it and validate the sanity of the restore.
Pardon my ignorance, Dipti. I can't imagine how long it must take to perform a full backup of a database of this size. What would a full backup, or how long would a full backup actually take? And is it possible to do every day?
Yes, we were doing it every day. It took less than 3 hours for full backup. So it was like 2 hours, 50 minutes, something like that.
And is that because all of the nodes are participating in the backup?
Yes, yes, all of the nodes are participating in backup and workload is going on. And without impacting the foreground workload, is backup going on. That's why.
My goodness. So the disk stores you mentioned,
Mm-hmm.
the fact that we were running 2 stores per node, I'm
Mm-hmm.
guessing is that's, and with write ahead log failover, that's the reason we're able to detect the slowdown ourselves and failover to the secondary store. But if you're not prepared, or you aren't aware of the frequency of cloud provider attached storage stalls, your application is just going to be stalling constantly.
Yeah, yeah, and you are going to see tail latency spikes every time there is a distalls.
Yeah. Well, thank you very much for sharing that. That takes us to our key takeaways. Now, before we do, I do want to see the polling questions. We did have the results for those, but they seem to have disappeared from my screen. If it's possible to get them up again, that would be lovely. But if not, the results were wild. There were people who were quite a few people in the audience here. Oh, thank you very much for that. So many people, probably about half of the attendees, just under half, are running up to 10,000 requests per second, up to around, looks about 30% of people are up to 100,000 requests per second. A smaller percentage then are up to 1 million. And actually, the greater percentage of those are seeing over 1 million requests per second for either their entire estate or for their busiest workloads. And and interestingly, there are people don't necessarily. Oh no, I didn't. I needed to scroll down. I thought, oh, there isn't anything over 1 million in a couple of years, but no, there is, and it grows. Probably about twice as many people reckon they're going to have over 1 million requests per second workloads in the next couple of years. I think that's staggering. So we ran a state of resilience report last year, and we ran a state of AI in data infrastructure report this year. And we found that 83% of companies reckon their data infrastructure is going to fail under the weight of agentic traffic in the next year to 18 months. And that's all because of AI. And without the right tooling in place, I think that scaling data infrastructure to cope with this is going to be an enormous challenge for development teams. We saw at the start that distributed SQL combines the best features of relational, NoSQL, and cloud paradigms. And we can now support 300 nodes, totaling, I'm guessing, with the ability to support a recommended maximum of 64 vCPUs per node, 19,200 vCPU node clusters, which just seems bonkers, and run multi-petabyte relational databases at scale. Now, as a thank you to everyone who's joined us today, we are giving away a free e-copy PDF of our distributed SQL definitive guide, of which I'm very proud to have played a small part in. So scan that QR code and you can download the book for free. But with that, the QA turns to us this time. If any of you have got any questions, and didn't ask them during their webinar, now's your chance. We've got a few more minutes left, but otherwise we'll give you your time back. But if there aren't any, I'd just like to thank you all very much for attending. Dipti, thank you so much for all of your insights.
Thank you for
And
having me.
no, it's been an absolute pleasure. Will we get a physical copy, as said in the email? Oh, that's a good question. Oh, yes, you can see the QR code again. And while I'm doing that, I would appreciate if someone from our side could tell me if about those physical copies. Oh, someone is typing an answer right now. You'll see it in a second. The physical copy is a beast. Are vector embeddings replicated across regions? Vector embeddings are replicated in the same way that all of the rest of the data is. The only thing that differs is the way the data is indexed. Now, we invented a vector index algorithm for this. We call it CSPAN, which is inspired by a bunch of well-known vector algorithms like SPAN, but also using things like rabbit quantization or rabbit queue quantization to shrink the size of the vectors before they go into CockroachDB at a cost of, you can store a lot more vectors, and the accuracy is only ever so slightly altered. But we've run tests of billions of vectors. So yes, they are replicated across regions. You can geo-partition vectors as well. So yes, everything you can do with regular data, you can also do with vector data. Now we got back to that question, so that was good. We're looking at the QR code again. I don't see any other questions. So with that, thank you all very much. That's the end of the webinar. We are going to have a survey in the next couple of days. If you want to see more of this kind of content, if you've got any feedback, positive or otherwise, we'd love to hear from you. Thank you all very much. Enjoy the rest of your days and evenings. Take care, everyone.